Hi everyone. Sorry about the video cutting off. We're right in the middle of explaining why the set of all possible multiples of 103 was a subspace. So basically you had U, which I can't remember exactly the notation I used, let's say 103, and you wanted to show that, maybe it was R, I don't remember, that it was closed under scalar multiplication. So this characterizes any vector that's in our set S. Now, if you want to show it's closed under scalar multiplication, take a scalar, multiply it by U. So that would be RC 103. But RC is a scalar that's multiplied by 103. So RU is in S. Okay, and thus it's closed under scalar multiplication. Now, the one that I wanted to get to, the problem in the notes that I wanted to get to that would be highly relevant to us is this one. The set of all functions y such that y prime plus y is equal to 0. Now, this is kind of the bridge between linear algebra and differential equations. Okay, so let's take a look at this. We want to show that this right here is a subspace. And subspace of what? And it's really the set of all functions, y equals function of x. Okay, these are just the ones that happen to satisfy that y prime plus y is 0. Now, to do that, we're going to establish two elements in S. So let y1 and y2 be in S. Okay, so what that means is that y1 prime plus y1 is equal to 0, and y2 prime plus y2 is equal to 0. And we want to show that y1 plus y2 is also in S. Okay, so what we need to do is we need to show that the sum of y1 and y2, so show y1 plus y2 is in S. So that means, in other words, show that y1 plus y2 prime plus y1 plus y2 is equal to 0. Okay, pretty simple process right here. We know from the very first week of class that the derivative is a linear operator. So the derivative of the sum is the sum of the derivatives. So that's y1 prime plus y2 prime. This is y1 plus y2. That equals 0. So I can reorganize this. So I have the y2 prime and the y2 together, and the y1 prime and the y together. Okay, now by assumption, this right here is equal to 0. By assumption, this right here is equal to 0. Okay, that's what it meant for y1 and y2 to be in S. And 0 plus 0 is 0, so this is a true statement. Therefore, y1 plus y2 is in S, and thus S is closed under addition. Now, the follow-up problem in the notes asks what happens if this were 3 instead of 0. Okay, if this were 3 instead of 0, then y1 prime plus y1 is 3, y2 prime plus y2 is 3, and by assumption, this is 3, and this is 3, and 3 plus 3 is 6, not 3. And so y1 plus y2 would not be in S, and thus that set, the set where y prime plus y equals 3 is not closed under addition, and therefore is not a subspace. Okay, so we're kind of doing both problems, both versions of this problem all in one. Okay, so there's something special about this being 0. Okay, so we're closed under addition. So I'll say closed under plus. So now, what happens for scalar multiplication? So let y, b, and s. Okay, and that means that y prime plus y is equal to 0, and show that ry, so r is a real number times y, is also in S. In other words, what we need to do is we need to show that ry prime plus ry is equal to 0. Okay? Well, to do that, ask yourself, when you take the derivative of a function times a scalar, what effect does that scalar have on the derivative? And the answer is nothing. It's the derivative of y is y prime, the derivative of ry is ry prime. Plus ry is equal to 0. You can factor out an r. Y prime plus y is equal to 0. By assumption, this is equal to 0. And therefore, we have a true statement, 0 equals 0. Good. So that means ry is also in S. Therefore, we're closed under scalar multiplication. All right. So that was the last problem that I wanted to go through with you today. I know there was one more in your notes, the set of all polynomials of the form cx squared plus d. But, well, I guess we can talk our way through it. If you're looking at polynomials of cx squared plus d, what kind of polynomials are you looking at? You're looking at quadratics with no middle term, but you're also looking at constant functions because you can let c equal 0. Okay, so if you have a quadratic that's cx squared plus d and another quadratic rx squared plus s, and you add those together, are you going to get something that is of the form constant times x squared plus constant? Okay, and I think you are. Okay, because even if the two constants of the two on the x squared terms cancel each other out, and you're left with the sum of the two functions equaling a constant, that is of the correct form. So I believe this set is going to be closed under addition. And now take a look at multiplying by a constant. Okay, so ry, which is rx squared, rcx squared plus rd, is that of the form constant x squared plus constant? Yeah, so you're closed under addition, or scalar multiplication. So I'll leave that one for you to write up, but you basically have a talking proof on that one. Okay, so that's the last little bit that I needed to clean up due to the video being cut off early. Sorry about that. Take care and have a great day.